Okay, so I'm here today to review the third lecture of an inductive summary of physics by Professor James Ellias. So that's what I'm going to be getting into today. I'll be going over each of the integrations he makes, the MQIC method he provides, as best I understand it, and then I will go through some things that I found interesting, as well as some questions that I have about the process. All right, so we'll jump in. So the first integration he talks about in this lecture is the pendulum bob and weight. Basically the relationship of the period of the pendulum and the weight of the bob that's on the end of the pendulum. So the idea here is that given that amplitude does not affect the period of the pendulum, maybe the pendulum will allow us to compare the bobs. So question then is, does the weight of the bob affect the pendulum? Basically, the investigation portion is to just do this experiment, and the conclusion you come to at the end of it is that this is not affected, the period of the pendulum is not affected by the weight of the bob. Now, in the process of doing the experiment, it's noted that we need to minimize friction, or at least make sure it's the same in each case, and this is done essentially by making sure that the bobs have the same size. I liked the discussion of the pendulum now being able to be used as a technology for timekeeping. This idea that it has a constant period means that you can use it as sort of an alternative to a water clock at the time is quite interesting, and I do think instrumental to the development of larger, more advanced timekeeping devices. So some questions I had. I'm not entirely clear what actually isolates friction in this experiment. James mentions that we keep the bobs the same size to isolate friction, but just thinking about an example of this, I'm not sure that would work if the bob was made out of, say, styrofoam. So there's something else to actually isolating the friction, and it's not just a matter of keeping the bob the same size. Now, Galileo wouldn't have had styrofoam, but I do think there's more to it than just keeping the bob the same size. Next one we'll look at. Minimize this for a minute. Maybe. Oh, there you go. Pendulum period depends on the length. So basically what we're going to find is, how does the pendulum period, what changes can we make to the pendulum that will actually affect the period? And it turns out one of the things we can do is change the length. So that's what we'll look at. Now, longer length, the idea is that longer length would mean a longer path of travel. So the question then becomes, will the longer path of travel result in a greater period? Again, we do the experiment, many different pendulums with different lengths, same bob attached, want to keep things the same. And it turns out that we find that period varies as the square root of length. So basically, you take the square root of your length, multiply that by some constant, and you will get your period. Now, I did like how this is covered after the test of amplitude, so we can know in advance that amplitude is not going to affect the period. Like it's very good to know that, because then amplitude isn't something we need to be as worried about keeping constant if we already know in advance that it doesn't actually affect the period. So some questions I had. Do you think this would be a good opportunity for some simulated data and for students to do a different type of linearization than they've done before? Square root linearization is a bit different than a squared linearization or a cube linearization, which you would have done with Kepler's law. in the meaning of the two in terms of units. So the equation we get in this from this integration is that the period equals 2 times the square root of the length. Now, that 2 has big implications. It turns out it's not exactly 2. It's pretty close to 2, but it does have big implications in the sense that it's basically converting the square root of a length into a time. So what units does that 2 need to have, and what is that going to mean for you know, the conversion factor when we actually do derive the full equation for this. So that there's some information embedded in that too that I think is worth bringing up, especially since units do come up in later analyses. Integration 20 was the rate of freefall. So pendulums are not affected by weight. The question then becomes, will heavier objects fall faster? Pendulums did not have a faster or longer period depending on weight, but will heavier objects fall faster? The idea is that they wouldn't, because pendulums work due to gravity. So maybe that's the thing we're going into this thinking. So in the investigation, basically what we need a way to sort of isolate and abstract away from the resistance that a falling object would feel. Now, the most common ones are friction and drag. It turns out that another one is the buoyant force. Now, the buoyant force plays effectively no role in when we have very dense objects dropping through the air. Plays more of a role if the object is less dense. But it plays a much bigger role if we drop a heavier object through water. Now, the buoyant force is brought up here. I do have a question about that later, so I'll leave that there for now. The conclusion is that the weight does not affect the time that it takes the objects to fall. So basically, two objects of two different weights. If we've isolated the forces that resist motion, if we've made sure that those things are affecting these two objects approximately equally, then weight does not affect the time it takes the object to fall a particular distance. So, kind of an interesting thing to note there. I like the connection of the pendulum to free fall. I like encountering these in tandem, and given that the way the pendulum works, it does depend on the way that it does depend on the rate of acceleration due to gravity. So the rate of acceleration under free fall. I like that. I like making that connection. Do have a few questions about this one here. Given this context, what's the pre-existing notion of what should happen and why? So a lot of people they bring up the example of, well, heavier objects will fall faster because they compare like a ball to a feather. Okay, fine, but there's something clearly different going on with the feather, because it's not just falling; it's doing this bobbing back and forth thing. Was there a better comparison? Like, had people done wooden balls and rocks, say, or wooden balls and iron balls? So what was the pre-existing conception of what would go on? Now, even at this point, I'm still a little unclear how to make sure we're effectively isolating friction. That's not entirely. I'm not entirely sure how we know that friction is isolated just from what's presented here. One last thing I did have a question about. There's a digression during this integration into how Galileo had a confusion between the forces of buoyancy and the forces of drag and friction. That's a somewhat interesting historical point. I don't really understand why it's brought up in this context. It's it actually serves to sort of derail the discussion. It distracts from, one, the ways in which Galileo did isolate the resistance forces, and two, we've not brought up buoyant forces at all at this point. Maybe some more advanced students will know what's going on here, but I really don't understand why this is brought up here, because I do think it is distracting. Okay, next one is the equation of free fall. So the idea here is objects gather speed as they fall. How much distance does an object traverse as it falls? This was the question. I was a little confused by this question because it seems like this question has an obvious answer to me. It will traverse the distance until something stops it. That is how far it will go. So if you're dropping it from 2 meters above the ground, it'll traverse 2 meters. So that I was not entirely clear on the question. And then the investigation was actually measuring times from different distances. So it was not a question about answering distance. It was about using a predefined distance and measuring time. So the basic conclusion then is that objects fall according to the formula d is equal to 5t squared. Assuming, of course, that we were using meters, which we would certainly not, Galileo would certainly not have been at this time period. So some memorable aspects. I did like the use of simulated data here. I think that would actually make for a very good exercise for the students to do. I mean, time to fall and distance fall, those are both very easily conceived things that they can grasp, and then they can graph it and they can do the linearization. I think this would be something really good to do sort of in advance of going over this. Some questions I had. The analysis here, it depended on having all those distances be conveniently divisible by 5. It's not nearly as clear what to do if, say, you would have needed to divide by well, let's just say, 11.74. Then the pattern would not have been nearly as clear. And you want to have a method. You want to present a method that doesn't depend on having that easy division right at the beginning. At least I would think you do. There's also at one point in this sort of a broad critique of the sort of traditional way methods of teaching physics are done. And the argument here is that in the traditional method, the equations speak for themselves, and it's not important to understand what each term is doing in the equations. I'm not entirely certain that's warranted. Whenever I asked those kinds of questions of people teaching me physics, they were always able to tell me what these different terms in these equations meant. It wasn't like I was never told it's unimportant what this V0 V naught T term does. I was never told that the coefficients are just sort of speak for themselves, and there's no interpretation to be gathered from them. I was always told that these things do mean something. Now, it's plausible that my experience was unique, but I don't think it's methodologically embedded in the teaching of physics that these equations speak for themselves, so to speak. So I would question whether or not that is actually warranted. So objects fall with a constant acceleration. That is integration 23. The motivation is we can see that falling objects speed up as they fall. The question then is, does the speed increase by the same amount each second? So that's the question we would want to ask. And the way I understood the investigation is we're going to assume that that's true, that the velocity increases by the same amount, increases by this amount a each second, and see if that data is consistent with what has already been observed. So it sounds to me like we're going to hypothesize that v equals at is correct and see if that's consistent. Now maybe I misunderstood what was going on there, but that's the way I interpreted it. And the conclusion is that if a is equal to 10, then yes, it is consistent. That v equals at is consistent with what we've already observed. So some things that I thought were good here is that I do think, particularly if you don't want to just equation push, you do need to bring in the idea of average velocities here. Really, it's given that average velocities are the things you can measure or you can calculate when you're just doing position measurements. Bringing in average velocities is quite important here. Now, the questions I have about this, there's a lot that just does kind of seem to be jumbled here. So the main thing that stuck with me is it seems like this idea that average velocity would then be equal to 1/2 acceleration times time. This comes off as being an assertion. That it basically, if you're going to use that assertion, you're kind of already assuming that your initial hypothesis was correct. So I guess I would be careful about doing that, particularly when the investigation hasn't been done yet. Like it's not clear to me where that ultimately comes from and whether or not that has yet been proven at this point. So the jumping off of that, I do think that constant accelerations and the patterns associated with constant acceleration, namely what the average velocities look like under constant acceleration, could be done fairly easily with ramps. And you have the connection to Galileo's cradle that Galileo had already been doing. And if you just have a ramp that where you measure the velocity when it comes off the ramp and it's no longer speeding up or slowing down, you can start to get these connections between velocity, time, acceleration, and then also displacement. So you can change the length of the position, distance, whatever. You can change the length of the ramp. And you can really start to put together the patterns of constant acceleration, and then you can connect that to free fall, and note that objects do in fact fall with a constant acceleration. It makes sense that they would, given that an object rolling down a ramp occurs with constant acceleration. But I do think that given the new concepts being introduced here, that a acceleration, average velocity, that some work where you could actually measure the velocity at the end using a ramp would definitely be warranted. The other question I have, and this is more a not really a methodological thing in the approach, but just what are you assuming about what the students know coming in to this? So in this integration, James goes off on a bit of a digression into what a function is, and in my view, the knowledge of a function is something that students should definitely enter the class knowing. Like that should be part of the context of knowledge when you're studying an algebra-based physics class. The problem is if it's not, if you're trying to sort of prove functions as well, well, the issue then is that one, that breaks up the physics, and that just makes it a little bit harder to connect back to what was going on with all of the physics. And two, the explanation of functions has to necessarily be brief because you have to get back to the physics. So if either the students will know what functions are, and you can use the idea of functions, or they won't, and you have to teach it. So this sort of tries to split a middle ground, and as a consequence, I think both things are hurt. I think the coverage of functions is kind of short and cursory, and the physics is broken up by this digression into functions. So this should be kinematic equations, but kinematic equation, fine. Basically the idea here is we want to generalize the findings of constant acceleration. And so what are the equations that relate the kinematics quantities? Now, in general, the kinematics quantities are position, velocity, and acceleration. And given that position and velocity can both change, we may need to have delta positions or delta velocities or initial and final velocities in those equations. So the basic idea here behind this integration was to explain how the kinematics equations could be modified. First, the velocity equation, v equals at, could be modified to incorporate some initial velocity, just add that initial velocity on. And then how the distance time equation could be incorporated, or could be modified to incorporate an initial velocity as well. And basically, the argument there is that the v naught t term is sort of what the object would do if it were undergoing just a constant velocity. So it has that sort of as its baseline. And then the acceleration is sort of this extra that gets added on top of it. So basically, at the end, we get the distance time and velocity time kinematics equations. So I do really like this coverage of what each term is doing in the equation. I think that's very important. There are many different ways that can be expanded upon, particularly graphically. That's another way that could be done. But I do like the idea that all these things mean something. So some questions I have. The explanation of what, say, the v naught t term is doing in the distance time kinematic equation, it's plausible. And I know it's true, knowing what I know about physics, but is that explanation proof? And if so, why? I'm not convinced that is necessarily proven. Like it makes sense, but why? Why does that constitute proof? Like, wouldn't we need to test that in some way to see if that is actually how it works, or whether or not we're overlooking something? So I think I might need to understand a little bit more about what it means to be proven in this situation, because I'm not entirely certain that it is proven. And if so, I'm not certain why. So it's also worth noting that, this could be investigated. It could be investigated experimentally. You could again do this either with ramps. Ramps are probably the easiest way to do it. But using a number of different methods, this could actually be investigated. And I think coverage of how it would be investigated is worthwhile, even if you're not going to go into it completely. Then the last thing I had was the time-independent equation. Now, getting at what the terms in the time-independent equation mean that's trickier. That I think is actually more understandable in terms of energy. But nevertheless, the time-independent equation can be derived from the distance time and velocity time equations. Now, in my then I guess I come back to the question, given that you can do an algebraic elimination and get the time-independent equation, does that make the time-independent equation proven? In my mind, it does, because it follows inexorably from the distance time and velocity time equations, which ostensibly at that point have been proven. So would the time-independent equation be proven by doing an algebraic manipulation, or does something more need to be done? Next integration was ballistic motion. So this phenomenon of objects moving forward while falling was a common phenomenon in this time. Any projectiles, bullets, cannonballs, arrows, whatever, underwent this kind of motion, ballistic or projectile motion. Question is, can the kinematics equations be used to predict this motion? Basically, the investigation was to use a ramp to generate a constant horizontal velocity, have the ball or object roll off the ramp onto a horizontal surface, and then launch off the horizontal surface and turn itself into a projectile. And it's shown that by separating the kinematics equations into a vertical component and a horizontal component, we can predict what the ballistic motion is going to be. Again, very good to note the need to neglect air resistance, and the idea that air resistance does become greater with greater speeds. So that is something that I think was probably recognized, but I'm not sure would be proven. So I consider that a question as well. A question I had is it's sort of presented as a fait accompli that we need to separate these into a horizontal and a vertical component. Is it obvious, given that it's a single projectile, that gravity is not going to affect anything about the horizontal direction? If it is obvious, why? It doesn't seem obvious on the face of it, having solved millions of physics problems where that's what you do. It's kind of obvious to me now. But thinking back to when I solved my first physics problem, it wasn't necessarily obvious that gravity wouldn't make the thing go faster in the horizontal direction. Saying it doesn't really make a lot of sense, but I do think that needs to be fleshed out a little bit more. And then the idea that you can actually measure the velocity after a rolling object hits the horizontal surface. You can measure the velocity by measuring the time it takes to go through two fixed points, because you know that on a horizontal surface it will just be going a horizontal velocity, or a constant velocity. So you can actually use the ramps to measure velocities. I feel like that would be beneficial to this, because you could also show that the horizontal distance traveled did prove that this horizontal velocity wasn't changing if you could measure the time it took to fall appropriately. Next integration is angled launch and ballistic motion. So shooting a projectile at an angle makes it go further. Can the kinematics equations be used to understand angled launch? And then basically we're going to use the vertical and horizontal kinematics equations again, while splitting the launch velocity into two components. And separable kinematics equations can be used to solve this. I really liked the example of swimming in a stream as an example of the separability of velocities. That if you have a downstream motion of a stream, you swim horizontally across it, the net effect is that you're going to go kind of diagonally. So I liked that example a lot. I think that's a good illustration of how velocity is a vector. A question I have: the next integration is going to be velocity as a vector, but aren't we already thinking of velocity as a vector just by breaking it into these two components? Like, isn't that effectively what we're doing here? Maybe I'm missing something about what's going on, but that was a question I had. Another thing that came up is the need to calibrate this using horizontal launch. And basically, the idea is that, again, you'll launch it from an elevated position, do it horizontally, you'll calibrate with that, and then you'll change the angle and do it with an angled launch. Now, the basic need here was I believe it was in order to figure out the initial velocity of the launcher. Couldn't this be done with vertical launch? Couldn't you do this by measuring the height and or the time of the ball to land if you launched it directly vertically? I do think additionally this would negate the need to launch from an elevated position, and thus would make the problem a little bit simpler. I did notice in the final derivation I didn't see the h when in coming into play, which I believe it should have in the y equation, because you should have had a change in your overall y position if you're launching from an elevated location. So, a couple of questions there. Last integration is that velocity is a vector. So basically, distances combine differently depending on direction, meaning that if you change direction, your total, and you take a right turn, the total displacement you've traveled from your starting location, it depending on how far you turn, whether or not you turn. If you turn 180 degrees, you're going back the other direction. So these distances, it does depend on, if you want to know the total distance you are from your starting point, we call it displacement, it does depend on the directions you move at different times. So the question is, do velocities combine in this way as well? Do they combine vectorially? And the basic idea behind the investigation is that fundamentally you can think about velocities in terms of distances. So if you're going off at an angle at a certain velocity, basically that's the same as going horizontal at one, or we'll say right, at one velocity and then up at another velocity. And it turns out that, if you're going to keep the times the same, that means the velocities combine in a very similar vectorial way. So because velocity is a vector, because position is a vector, basically what's going on here. I liked the relationship of velocities and distances. This is obviously a connection that needs to be made. Airspeed, an example, was interesting. It shows it in visual form, in vector form, which was good. I don't know if the context includes vectors yet, but nevertheless, this was a good way of demonstrating that. So the main question I had is, could this velocity as a vector be done earlier using just basic speeds and distances? So thinking about it this way, if you're going at 30 degrees north of east at 5 miles an hour, can you split that into, that's the same thing as going east at a certain, east at the horizontal component, or the eastward component, and north at the northward component for the same amount of time. So that was a question. I feel like this, you don't need to wait until after you've done the kinematics equations to prove velocity is a vector. You can do that before. And I think it actually might be useful to know that, because, like I said before, it's my sense that breaking velocity into components requires you to be thinking of velocity as a vector at that point already. But I would be happy to hear otherwise. In any event, that is it for this review. That was it for this lecture. So thank you for tuning in. I will see you next time.